Hello guys, welcome to my channel. So today we are going to discuss about introduction to VLSI and VLSI fabrications. Very large scale integration is a process of creating integrated circuits by combining millions of transistors on a single chip. This complex fabrication process involves a series of intricate steps to produce the tiny, powerful semiconductor devices that power our modern electronics. So actually we have a very large scale integration. So here many millions of semiconductors are placed in a single chip and it forms the semiconductors or integrated circuits. So wafer preparation, silicon wafer production. Silicon wafer, the foundation of VLSI chips, are meticulously produced through a series of precision processes to ensure consistent quality and purity. Wafer cleaning, rigorous cleaning techniques such as chemical baths and plasma etching are used to remove any impurities or defects from the wafer surface. Then we have surface polishing. The wafer surface is polished to an automatically flat finish, creating an ideal foundation for the intricate layers of a VLSI chip. Then photolithography process. We have mask preparation, wafer coating, exposure, development, etching. We have mask preparation, creating a precise photomask with a circuit pattern. Then wafer coating, applying light-sensitive photoresist material to the wafer surface. Then exposure, selectively exposing parts of the photoresist to ultraviolet light. Then we have development, removing exposed photoresist to reveal the pattern. And we have etching, removing the unwanted material from the exposed regions. Then the photolithography process is the cornerstone of VLSI fabrication, allowing for the precise transform of circuit patterns onto the semiconductor wafer. By leveraging the light sensitive nature of photoresists, this multi-step technique creates a replica of the desired design, which is then used to selectively remove or deposit material, forming the intricate structures. Then this firm deposition, thin film deposition is a critical process in VLSI fabrication. It involves the controlled applications of thin layers of materials such as metals, dielectrics, and semiconductors onto a silicon wafer. This process is used to create the intricate circuits and interconnections that make up integrated circuits. Various deposit techniques are employed, including chemical deposition, physical vapor deposition, and automatic layer deposition. The choice of technique depends on the specific material and the desired characteristics of the thin film. And etching techniques: photochemical etching, plasma etching, and wet chemical etching. This precise process uses light-sensitive chemicals to selectively remove materials from the wafer surface, creating intricate patterns. Then highly reactive plasma is used to rapidly etch away materials, enabling anisotropic etching for vertical high aspects ratio features. Then wet chemical etching. Immersion in liquid chemical baths can isotropically etch materials, useful for creating undercuts and releasing structures. Then ion implantation. Ion implantation is a critical step in VLSI fabrication, which where high energy ion beams are used to introduce precise concentrations of impurities into semiconductor materials. So this process precisely controls the depth and distribution of dopants, enabling the creation of complex inter- integrated circuits structures. By carefully tuning the ion beam energy and dosage, semiconductor manufacturers can selectively dope targeted regions of the wafer, forming the active components such as transistors, resistors, and capacitors that make up the integrated circuit. Oxidation and diffusion. Oxidation, controlled growth of silicon dioxide on silicon wafer surface. Diffusion, impurity atoms introduced into semiconductors to control doping. Then I have thermal processes, high temperature treatments to enable oxidation and diffusion. Oxidation and diffusion are critical thermal processes in VLSI fabrication. Oxidation involves the controlled growth of silicon dioxide on the silicon wafer, which acts as an insulating layer. Diffusion introduces impurity atoms into a semiconductor, enabling precise control of doping levels. These high temperature treatments are carefully authorized or created to desired device characteristics. Then metallization and interconnectors. Interconnects. Thin film, thin film deposition. Metals like aluminum, copper, or tungsten are deposited on the wafer surface using techniques like sputtering or evaporation to create the conductive interconnect layers, patterning and etching. The metal layer are patterned using photolithography and etched to form the desired interconnect structures connecting different components on the chip. Then multi-level interconnects. Modern VLSI chip utilize multi-levels of metal interconnects stacked vertically and connected through vice versa to increase wiring density and reduce single delays. Then I have dielectric insulation. Insulation dielectric materials like insulating and dielectric materials like silicon dioxide or low key dielectrics are dependent between the metal layers to prevent crosstalk and ensure single integrity. Then I have packaging and assembly. Packaging and encapsulation. The fabrication chip is packed into a protective house, often made of ceramic and plastic. The shield it from environmental factors and enable electrical connections to the outside world. Bonding and interconnects. Fine gold or aluminum wires are used to create electrical connections between the chips, pads, and package leads, allowing to signals to transmitted in and out of the devices. Then I have assembly and testing. The packed chip undergoes rigorous testing to ensure its functionality and reliability before being integrated. The final electronic produces ready for end user application. Then I have challenges and advantages in VLSI fabrication. Miniaturization, miniaturization and challenges, innovative materials, lithography advantages, and automation and AI. As VLSI features continue to shrink, the industry faces daunting challenges in maintaining nanoscale precisions, controlling heat and power density, and mitigating quantum effect that disrupts device performances. Then I have innovative materials. Researchers are exploring new semiconductor materials like gallium nitride and carbon nanotubes to overcome the limitations of silicon. These advanced materials enable faster, more energy efficient chips for emerging applications. Then I have lithography advancements. Cutting edge lithography techniques like extreme ultraviolet and electron beam lithography are enabling the manufacturers of ever smaller features, pushing the boundaries of what's possible in VLSI fabrication. Then I have automation and AI. Intelligent automation and machine learning are transforming VLSI fabrications, optimizing complex processes, predicting defects, and accelerating the path from design to manufacture.